Okay, 1220, worksheet 1220. Same assignment number as the last multiple choice one, but these will count as separate assignments. These are free response problems. You should have tried these already, and we'll go over them now. So, first problem is a graphing calculator problem, by the way. So, sorry if that messing one up. It is a graphing calculator problem. Point breakdown is going to be 3, 1, 2, and 2 out of 9 points. Let's see if I can fix my sunlight problem. Okay. So, a cylindrical can of radius 10 millimeters is used to measure rainfall in Stormville. The can is initially empty and rain enters the can during a 60-day period. The height of the water in the can is modeled by the function S, where ST is measured in millimeters and T is measured in days, 0 to 60. The rate at which the height of the water is rising in the can is given to you by S prime. So they give you S prime. I mean, this kind of sounds like a rate model problem at first. I don't know, there could be some related rate stuff in it, maybe too. Let's see, it says, according to the model, what is the height of the water in the can at the end of the 60-day period? So, according to the model, what's the height? So this is they give you S prime. Now, we could work backwards to find S, but I think it would just be easier to treat it as a rate model and say, okay, well, the amount is S. Now, instead of using capital M, use capital S because that's what they're using, would equal the amount at some time 0 plus the integral from 0 to time t of the entering amount minus the leaving amount. There is no leaving amount. Rain is falling into. There is no initial amount. It's 0. So if you want to know S60, it's just going to be 0 to 60 of the integral of S prime t dt. And we can just do that on our calculator. Now, on your calculator, I'm going to put it under the Y menu. And we're probably going to have to do multiple calculations with it. So that's what I'm just saying. It'd be helpful. 0.03x plus 1.5. I'm not graphing it. I'm going to go back to the home screen and go math 9, bars, y bars function, y1, comma x, comma 0, comma 60. So we get 171.813. The units, let's see, the units are millimeters, right? Millimeters. So 3 points, 1 point for the limits, 1 point for the integral, 1 point for the answer. So that wasn't too bad. Part B says, according to the model, what is the average rate of change in the height of the water in the can over the 60-day period? Let's see. Show the computation that leads to your answer. So S is measured in millimeters. So S is the height of the water. And so if you want to know, it says, what is the average rate of change of the height? So they're looking for S prime average rate of change of the height. S prime is the rate of change, and we're going to do the average. Now, since this is a derivative, it'd be easier to just go with the mean value theorem that we learned for derivatives, which is it's just the slope connecting the endpoints of a secant line on the original function that you're trying to find the average slope of. That's probably easier. And by the way, we just found S60. That's convenient, 171.813. And I'm going to write a couple extra decimals here just because we're using it to calculate something else. I'm glad I didn't lose it. still have it. Minus the height at time 0 was 0, or 60 minus 0. So that's going to be just my previous answer divided by 60 is 2.863 or 2.864 round truncated through decimal place. Actually, the units of the top are S, which are height, millimeters. The units of the bottom are time, which is days. Millimeters per day is the average rate of change of the height. So a little mean value theorem there. For derivatives, see, assuming no evaporation occurs, at what rate is the volume of the water in the can changing at time t equals 7? So we're trying to find the derivative of the rate of change of at what rate is the volume changing? So rate change of the volume at time equals 7. Now, I think this is where the related rate stuff comes in. So, I mean, you could always draw a picture. It's a cylindrical it says can, and it has a radius, constant radius of 10 millimeters, right? And then there's a level of fluid in it that has a height, which they're calling S, right? And so the volume of the liquid in here at any point is going to be, so we're trying to find this. It says, assuming what's the rate, at what rate is the volume of water changing at T7? It should be positive, I think, right? I think we're just gaining rain and there's no evaporation. So I'm assuming the model reflects that. So the volume of this is pi r squared times the height, right? The volume of a cylinder, you guys should know that, circle times the height. So if we want to do dv dt, now here's the deal. Before we take the derivative, we have a constant radius. So that would be helpful to plug in ahead of time because it's not changing. So the volume actually equals 100 pi h. And then when you take the derivative, you don't have to deal with the product rule and a bunch of mess. That would eventually work out also. You would just have to plug in dHdt at 0 at some point, or dar dt at 0 at some point. So this is going to be 100 pi dH dt. Now, at h, by the way, is s, right? So ds dt, which is s prime. And so at time 7 days, we're going to need s prime at 7 days. And so I think we could just write that down. And then on our calculator, I could go to the table, be a convenient place to calculate this table, and you put in 7, and that shows you the value. So this is going to be 100 pi times 1.916919,799. I think that's enough decimals. So back on the home screen, I'm going to do 100 pi times 1.916919799. Enter, and we're going to get 602.2181115. So that's where you change the volume. So dVdt at time t equals 7 equals 602.218. What are the units? Well, volume are going to be millimeters cubed. Time is in days. Just putting the units. They did say indicate units of measure, so you're going to lose points if you don't have it. Indicate units of measure on the previous problem. If you don't have it, you're going to lose points. Now, as far as points, part B, you got 1 point for the answer, and you needed the units on it. So I guess if you didn't put the units, you lost a point. Part C says is worth 2 points. So 1 point for getting DV, for getting this dVdt, and then 1 point for your answer with units. Part D is during the same 6-year period, rain on Monsoon Mountain accumulates in a can identical to the one in Stormville. The height of the water in the can on Monsoon Mountain is modeled by the function m. So this is a different one, and they're actually giving you the height of the water instead of the derivative. The height m is measured in millimeters and t is measured in days, just like that one, 0 to 60. Let dt equal m prime t minus s prime t. Apply the intermediate value theorem to the function d on the interval 0 to 60, justify that there exists a time 0 to 60 at which the heights of the water in the two cans are changing at the same rate. Okay, so they give you this new function for m, monsoon mountain. I'm just going to write this down just to have it right next to where I'm trying to do my work. And then they tell you that dt equals m prime t minus s prime t. And so they say to use intermediate value theorem to show that they're changing at the same rate. Now, if they're changing at the same rate, that means that it's got to equal 0, right? Changing at the same rate, because their derivatives will be equal to each other. And when you subtract one from the other, you get 0 because they're the same. So that's what we're trying to prove happens. Now, we don't, let's see, we don't really have an equation for, well, we do have s prime. I don't know. I feel like we could easily show this on a calculator. We could show where it happens. But I guess one way of using intermediate value theorem is you could say, well, what's the difference between them at time 0? And so we could calculate that. So we have this new equation that we could take the derivative of. So if we did math 8 and we type that equation in, 1 divided by 400, parentheses, 3x to the third minus 30x squared plus 330x, close, comma x, comma 0. So that's m prime at 0, 0.8250000075 minus s prime at 0. We could go to the table and put that in, and it's 1.5. So then we could go back to this screen and subtract 1.5 from this, and we get that it's negative 6.74999, which is negative, which means that the canon in S is changing more than the one in N. And then we could do it at 60. And so we could go back to the previous one and put a 60 where the 0 is. And that's the rate change of Monsoon Mountain, 72.825, minus, and we could go back to the table and put 60 in here, and it is 3.4476952661. And then we could go back to the home screen and subtract 3.4476952661, and that gives you 69.377304, which is positive. And so intermediate value theorem says that if these are continuous functions, that you have to hit all the values between. So if we know we were starting at negative and we're ending at a positive, then it had to go through 0 at one point, right? So, and they told you earlier that they said, okay, so we'd have to say something like, since D is continuous, that's the requirement for intermediate value theorem, the intermediate value theorem says that there must be a time t between 0 and 60 at which dt equals 0. So m prime t equals s prime t. The heights of the water in the two cans are changing. Changing at the same rate. So something like that. You want to name it. You want to state the conditions for it. So something like that. Now, I was thinking we could actually find this. Like, if we get a y, we could say, we could take the derivative of that ourselves. It wouldn't be too hard, right? So m prime is going to equal 1/400 is just in front, and then you get 9t squared minus 60t plus 330. And then we could put that into our equation here, 1/400, parentheses, 9x squared minus 60x plus 330. We go to window and go 0 to 60. I'm going to go back to the y here, and well, we could figure out where they cross by graphing both of them, or we could make a new equation, one subtract the other, and figure out where its x-intercepts are. But we go to window, we go zoom fit. Hopefully these aren't too big of functions. Oh, it's really big. Look how dense that is. And it looks like they cross way down here, so we could go back and change it. Our window is going to probably be huge in the y direction. I'm going to make y min -1, and I'm going to make this equal to 10. And so there's the first one. That's s prime, and then here, there it is. So you see where they cross right there? So I mean, we could actually find the time, so I can calculate intersect, first curve, second curve. Looks like it's around 10. And it's at 11.816 days. They both have the same rate of 2.194 millimeters per day. Anyways, just kind of an interesting way of forcing you to doing that. Okay. Now, point-wise, those were 2 points. Probably a point for calculating the work, setting up. Probably just for writing this equals 0 down was a point, and then figuring out this point. Next problem says a 12,000 liter tank of water is filled to capacity. At time 0, water begins to drain out of the tank at a rate modeled by RT, measured in liters per hour, where R is given by the piecewise defined function. So this sounds like a rate model problem. It's a 12,000 liter tank that's filled to capacity at time 0. So the amount at 0 is 12,000, right? And then this is the rate at which water is draining out. So this is a leaving rate, right? So I like to put a negative there. Is R continuous at t equals 5? Show the word glaze for your answer. Now, if they're asking you if something's continuous, then you probably need to use the definition of continuity on a free response question. So the definition of continuity, I'll just write down what it is we're trying to prove. The definition of continuity, and you're probably going to want to write it all out. I'm just going to write this as a little note to ourselves, is the limit as x approaches a of a function equals the function at a, so that there's no hole, it's connected, there's no jump. Now, to prove the limit, we got to prove the limit first, and we got to prove this second, and then show that they're the same. But to prove this limit, especially with the piecewise function, you have to take the two different sides. One side is for one side, and one side is for the other, so you got to do one-side limits. So we got to say, all right, well, the limit as t approaches 5 from the left side of RT equals the limit as t approaches 5 from the left side. Now the left side is left of 5 is this one, 600 t over t plus 3. And so what we get is we get 5 in there, so that's 3,000 over 8, which is 375. Now, by the way, this is a graphing calculator problem also. Okay, so then we're going to take the limit separately from the other side, 5 superscript plus, so that means from the right side, and we're going to say limit as t approaches 5 plus of 1,000 e to the negative 0.2 t, and that's going to equal 1,000 over, now you plug 5 in here, it's going to be e to the negative 1, so e to the first in the denominator, and if you calculate that on your calculator, you get 367.879, and these don't equal each other, so the limit doesn't exist, so there's no way for it to even be continuous for sure. Both sides are approaching different values. That's enough. If those were the same, we'd have a little more work to do. But we'll say RT is not continuous at t equals 5 since the limit as t approaches 5 from the left-hand side of RT does not equal the limit as t approaches 5 from the right side of RT. So there you go. So the point breakdown on this one's going to be 2, 3, 2, 2. So I don't have right now my finger. Well, let me see if I have what the point breakdown would be on this one. So it was conclusion with analysis. They just said conclusion with analysis. So I think that it's not continuous is a point, and the reason for that is that the one-sided limits aren't equal, but you needed to show what they were to support that claim. B says find the average rate at which the water is draining. Average rate. So we want average R, by the way, because R is the rate from 0 to 8 hours. Now 0 to 8 hours spans this chunk and this chunk. So the basic idea is that we're going to integrate RT, even though it's a derivative, we don't have the original function. So using the mean value theorem for derivatives doesn't make sense here. We're going 0 to 8, and we're going to smooth it out, find the area, make it a rectangle, divide by the base of the rectangle, get the height of the rectangle. Now, that setup is easy enough, but to actually calculate it, you're going to have to do 0 to 5 with that first chunk, 600t over t plus 3 dt, and then you're going to have to do the chunk from 5 to 8 separately. Now, you're still calculating that as one big area and then dividing by one big and treating it like one big rectangle. So it's important to write all this stuff down because this is where most of your points are. Having the constant and the limits correct is a point. Having the integrand correct is a point, and then your final answer is a point. So we're just going to do all this work on our calculator. I don't know if we're going to be doing other calculations with this, so I don't know if we need to maybe put these in our... We could do it. We could do 600x divided by parentheses for sure, x plus 3. And the next one is 1,000 e to the negative 0.2x. I don't know, just put them in here to make it quicker. So on this screen, I'm going to do 1 divided by 8, parentheses, math 9, vars, y vars function y1, comma x, comma 0, comma 5, plus math 9, vars, y vars function y2, comma x, comma 5, comma 8, close, close. This should do it. 258. 0.053. What are the units here? R is in liters per hour. So this is average R. So this is liters per hour also. Point wise, that was 3 points. Like I said, most of it was for the setup, 1 point for the answer. C, find R prime 3. Now, R prime 3, R is already a derivative. Now, finding R prime 3 isn't hard because we could just do math 8 bars. Now, 3, we got to use the first piece, right? So we're going to use y1, comma x, comma 3. And that's the answer right there, 50.000. The units are going to be liters per hour squared because R is already liters per hour, and this is the derivative of R. Okay, so that by itself wasn't too hard. That was worth a point just for doing that. And then they're probably going to ask us what it means. Using correct units, explain the meaning of that value in the context of the problem. So it has to be involved with the water tank and it's draining out. So this is the rate of change of the rate. So, and the fact that it's positive means it's increasing. That's probably a word you want to use. If it was negative, you want to say something's decreasing. So we're going to say the rate of the water draining from the tank is increasing. So the rate is increasing by 50.000 liters per hour or per hour squared. Per hour means the same thing. At time t equals 3 hours. So you want to be very specific. When is it? Put all the units. Talk about. So that's a point. So when you get a positive derivative of something, the best way to probably the most common way to explain that is that the rate, whatever it is, the derivative of is increasing or decreasing. And since R was already rate, the rate of water is increasing by this much. Okay, which means that the rate it's losing more and more water, right? D says write but do not solve. Please make sure you don't solve it. An equation involving an integral to find the time A when the amount of water in the tank is 9,000 liters. So it starts out at 12,000. So this is kind of like the rate model part of it. Like the amount of water in the tank is equal to the amount of water at time 0 plus the amount of water coming in, right? The entering rate minus the leaving rate. Okay, this is generally our strategy, right? Now for us, the amount at time 0 is 12,000. There is no entering rate at all, and the leaving rate is what R is going to be. So I'm going to rewrite this. The amount of water in the tank is 12,000 minus 0 to t of RT dt. So you want to make sure you use the names that they are using. I just wrote that simply first to kind of make me think, the way I usually think when I think of rate models. Now, we want to know, when is it 9,000? So we could say, well, it's going to be 9,000, and this is going to be 12,000 minus 0 to t of RT dt. Now, I think that would be fine. Yeah, totally fine. And so it's worth 1 point having this integral in here and 1 point just for the whole thing. It better be an equation, two sides. Better have an integral. Now this would be the easiest way. There are other ways of doing this. You could make this more complicated. You could say, all right, well, let's do 12,000 and then let's integrate from 0 to 5 of 600t plus t over t plus 3 dt minus 5 to, now, by the way, I messed up. You need to put a capital A. Capital A is supposed to be that what they said was the time. So using A here maybe was worse. It is a volume of type, so maybe volume would have been a better letter there, since we were supposed to use A for the time. And then 5 to A of the other one, 1000 e to the negative 0.2 t dt. Now, the only thing that you're running into issue here is this might be wrong, because it might happen in the first 5 hours. So it's a little sketchy. You could calculate what the amount is after the first 5 hours, just to make sure. So we could do 12,000 minus math 9 vars, y vars function y1, comma x, comma 0, comma 5, and this will be how much water is in there after 5 hours, and it's not quite enough. So you could do that. You could say, so that would give you the confidence to go ahead and write it like this, but then you could also write it like this. You could say, okay, well, I know it's not going to happen the first 5 hours, so we'll just put that amount in and then subtract 5 hours and on using the other part. Now, again, these are all necessary. You could have just done it like this, which is a lot easier. Okay? All right. Next problem. Table. You probably are going to use some kind of estimation techniques. Slope of a tangent line to estimate derivative. Riemann sums or trapezoids to estimate an integral. Very likely. Okay? No calculator on this one. Okay? No graphing calculator on this one. So we have this table, meters, and then meters per second. It sounds like position. It sounds like rectilinear motion. Ben rides a unicycle back and forth on a straight east-west track. So this is one-dimensional motion. The twice differentiable function b. Twice differentiable means the first derivative exists everywhere, which means the original function has to be smooth and continuous. It means the second derivative exists everywhere, which means the first derivative needs to be continuous and smooth. Function b models Ben's position on the track, measuring meters from the western end of the track. Okay, so this is a position from the western end of the track. Why is it so bright? Okay. And then t measured in seconds from the start of the ride. So only positive time. The table above gives values for bt, Ben's velocity vt, measured meters per second at select times t. Use the data in the table to approximate Ben's acceleration at time 5. Indicate units of measure. So time 5 would be like right in here. And if you want to estimate acceleration, that's the derivative of velocity. So we want to do, if we want to estimate the acceleration at 5, then that would be approximately a slope between the slope of the velocity line from 2 points as close to 5 as possible. So that would be velocity at 2.3 minus velocity at 2.0 over 2.3 minus 2.0. This is all work you definitely want to show to make sure you get credit for it. Now, velocity at, oh, you know what? I'm sorry. It's supposed to be time 10 and time 0. I was putting those values in. Now, the next step would be 2.3 minus 2.0 over 10. That'd be 0.3 over 10. That would be 0.03. And the units are, I did say, indicate units of measure. You're going to lose points if you don't, for sure. So I'm always putting units no matter what, because I don't want to accidentally forget when they tell me to. If there's units in problem, I'm going to put units. So this is going to be meters per second squared. You should know acceleration is meters per second squared. And that's your approximation for acceleration at 5. Now, the point breakdown here is 1, 2, 2, 3, and then 1 point for units on parts A and B. So if you didn't put these units, you put the wrong units, you lost a point. And then in general, this is just worth a point. Part B says, using correct units, interpret the meaning of the integral of the absolute value of velocity in the context of this problem, and then approximate using the left Riemann sum. Well, the meaning of this, you guys should know this. The integral of the absolute value of velocity is distance, right? Distance traveled is the total distance, not displacement, distance traveled, you got to put all the units in meters. That Ben rides his unicycle. It said in the context of the problem, so you should be talking about Ben and his unicycle, riding it from, and you got to say when, time t equals 0 to t equals 60 seconds. Now, if you leave any of those units out, you're losing a point. Okay, if you got to say total distance, traveled by Ben. Okay, now that's the first part. If it didn't have the absolute values, it'd be the total change in position, which we have a special term that we call displacement. Now, we also need to go ahead and estimate the value of that interval, 0 to 60 vt dt. Now, this is where we're going to draw a rectangle. It says using a left Riemann sum. So I'm going to draw a picture. I'm going to say, okay, 0 to 60, 0, 10, 40, 60. And then we're doing velocity. So it's 2.0, 2.3, 2.5, 4.6. And we're doing left Riemann sum. Now, does it say it's positive the whole time? It looks like the velocity is positive the whole time, but I don't think it means it is for sure, because unless they told you. So, and we're doing left Riemann sum. So we're not going to use this guy. The bases are 10, 30, and 20. So we need to show the work for drawing rectangles. So it's going to be 10 times 2.0 plus, and label it, please. Don't just start writing terms. 30 times 2.3 plus 20 times 2.5. So this is probably worth a point right here. Your picture isn't worth any points. Your picture is just to help you make sure you set it up right. Now, we don't have a calculator, so we're going to say, all right, well, this is 20, and this is, what's this going to be? 369 plus 50. So that's going to be 70. That's going to be 139. And the units are meters. So there you go. That's a point. I guess just 1 point for the interpretation and 1 point for the estimate. C says from 40 to 60, must there be a time t when Ben's velocity is 2 meters per second? Justify your answer. So we're trying to figure out, is there a time when Ben's velocity is 2 meters per second? And if you look at the table, it is 2 meters per second. Now, they said from 40 to 60. 40 to 60 is his velocity for sure, 2 meters per second. Now, I mean, intermediate value theorem isn't going to help us. Mean value theorem isn't going to help us. Well, actually, mean value theorem might. Yeah, I think mean value theorem might. Because remember, velocity is a derivative of position. So maybe if we find the average derivative of position, average velocity, if it's 2 meters per second, then remember there's that guarantee on the mean value theorem that the actual value will equal the average value at least once. So I think that's what I'm going to try. Intermediate value theorem. It's either going to be intermediate value theorem or mean value theorem. Intermediate value theorem, if this had a value lower than 2 and one greater than 2, then you would know it'd have to hit 2 in between. But that's not the case. So it's probably got to be mean value theorem. So V average is the same as B prime average, right? And so then that's going to be B at 60 minus B 40, 60 over 60 minus 40, and that's going to be 49 minus 9 over 60 minus 40, and that's going to be 40 over 20, which is 2 meters per second. So that's your average. So then, therefore, by the mean value theorem, Now, there are requirements in the mean value theorem, okay, to be applicable. The function needs to be continuous and differentiable. Now, the table on its own does not tell you that, but they told us earlier that b was twice differentiable. So we probably have to set up, we can say, since b is twice differentiable, and the average velocity between 0 to 40 to 60 is 2 meters per second by the mean value theorem, there must exist a time t on 40 to 60 where the actual velocity is 2 meters per second. So something like that. And I'm thinking you need most of that in some way or another. That problem is worth 2 points, 1 point for calculating, 1 point for just showing this, that you're even trying to mean value theorem, and 1 point for your conclusion with reasoning. Okay, D says a light is directly above the western end of the track, been ride so that at time t, the distance L between bin and the light satisfies this equation. Oh, this is crazy. There's a light, and then there's this relationship between the distance L between bin and the light. At what rate is the distance between bin and the light changing at time 40? So this seems kind of like a related race problem. We could try and draw a picture. There's a light, and then here's bin on his motorcycle, unicycle. And this would be the distance between the light and bin, and then this is the distance between bin and the western end, right? That's what BT represented originally. So it's like a right triangle. And the light is, does it say how tall the light is? It doesn't, but I'm assuming that it's this 12 right here. So this looks like Pythagorean theorem, right? Not that you need to know where it came from, but it kind of makes sense. So we're trying to find dl dt at time 40. So this is a related rates problem. We got to take the derivative of the relationship, which they already gave it to us implicitly. So it's going to be 2 lt dlt dt, or L prime if you want, equals derivative 12 squared is 0. So then this is going to be 2 bt dB dt dt. Now, by the way, this is velocity, right? The derivative of bin's position, b versus time, is velocity. So we're trying to find this. So dl dt dt equals, we can divide a 2 out of both sides, and then it's going to be bt times vt over lt, right? And let's see, what else did they tell us? So we want to know what it is at 40 seconds. So we want to know B40, V40, and L40. So B40 from the table up above is 9. V40 from the table up above is 2.5. And then what is L40? Well, it comes from this, right? So if you do L40 squared, it equals 144 plus B40 squared. Now B40 is 9 squared. 9 squared is 81. So L40 squared equals 225, and then take the square root of both sides, plus or minus. L40 equals 15, so that's what goes in here. And then finally, we get our answer. We could try and clean this up. I don't know. 3 goes into this 3 times, 3 goes in this 5 times, 5 goes in this 0.5 times. So it's going to be 1.5. The units are length over time, meters per second. Wow, that was challenging. That was worth 3 points. 1 point for doing the derivative implicitly, which I thought was pretty obvious. 1 point for understanding that dBdt was VT, I think, and getting this, and then 1 point for your final answer. So that was kind of a little bit of a tough one. I drew the picture, not that you had to, but it made sense once I drew the picture of what that equation was. But you could figure it out probably without having that understand. So there you go. Some good table problems, motion problems, related rates, Riemann sums, rate models, lots of different good stuff on there. So